But because we don't have access to the entire population, we have to make a guess about what the population mean would be. What is the material that we have at hand? The sample, the known variance of the sample, and the sample size. Now, given that for a minute, we hold the null hypothesis to be true. Like we hold the hypothesis that this person is innocent as a tentative hypothesis, and see if we get enough evidence to at one point say that, hey, look here, it seems extremely unlikely that this person is innocent. Yeah? And if you really want to, this is very important, okay, and if you really want to understand how complex and how interesting that process is, please watch a movie called 12 Angry Men. Have you watched this movie, 12 Angry Men? Or watch a Hindi movie called Ek Ruka Hua Faisla. Yeah, it's a version of the same movie. Sure? Okay, so but we'll come back to that. Right. So we have x bar minus mu upon, so we need to do that. Okay. Now if mu is truly the population mean, which is, if we, under what we have assumed to be true, x bar minus 5 upon sigma by root n must be a standard normal variable, right? So it must lie between minus 1.96 plus 1.96 95% of the times, 2.5% of the times a standard normal variable. Given our null hypothesis is true, we'll take a value less than 2.5, less than minus 1.96, 2.5% of the times, even when our null hypothesis is true, a standard normal variable will take a value greater than plus 1.96. So the sum total is, if our null hypothesis is true, the probability with which a standard normal variable will take a value either less than minus 1.96 or plus 1.96 is about 5%. 2.5% this way, 2.5% this way. Okay. So in this case, so what do? We substitute our sample mean x bar, yeah, in that formula. What is the number that you get? The number that you get is the z value. It is the value of the standard normal variable, x bar minus mu by sigma by root n. In this case, it turns out to be minus 3. In this case, it turns out to be minus 3, right? Now, how do you interpret this? Is this consistent with the null hypothesis, or is it not consistent with the null hypothesis? Why is it not consistent with the null hypothesis? Because if the null hypothesis is true, the probability with which the standard normal variable will take a value either less than minus 1.96 or plus greater than 1.96 is only 5%. So, there is only a 5% chance here that your null hypothesis could actually be true. That there is a 5% chance that your null hypothesis could actually be true.
So,
right?
Yeah. If you compare it with the value 1.96, what is probability of 0 and 0.5?
No, the probability is fixed. We are comparing with minus 1.96 or plus 1.96.
In case, it should lie between minus 1.96 and 1.96.
Because we have chosen a 5% values. I'll come to why we have chosen 5% values. Okay, once we decide to choose the 5% values, then you are committed to minus 1.96 plus 1.96. Okay, right? That's an important question. Why choose minus 1.96 plus 1.96 only? I'll come to it. Once I finish telling you how to interpret things with minus 1.96 plus 1.96, then we can go and talk about why 1.96. Okay. So suppose you have chosen these values, right? You got a z value, which is less than minus 3, which is minus 3. So you are saying that there is only a 5% chance that the null hypothesis is true. And by choosing the 5% cutoff levels, you have already predetermined, you have already made up your mind that if just a 5% or less chance that the null hypothesis is true, I am going to say that in all likelihood the evidence that I have is not consistent with the null hypothesis, and I am going to reject the null hypothesis. So this 5% chance is what you had decided beforehand as a benchmark. Like if you go to the case yesterday that we talked about, if your elephants are suffering from, we are identifying ill elephants, and suppose all ill elephants lose weight, right? Okay, and if the elephants are ill from a very, very contagious disease, so that if an ill elephant is not quarantined but left in the population, he will, the illness will spread, in which case you will be very, very careful about not letting an unhealthy elephant back into a population, even when in that process you have to carry some healthy elephants to the medical camp. You will say 4 healthy elephants आ गए तो भी चलेगा, but एक भी unhealthy elephant should not go back to the population because the contagious disease spread. In which case, just a 5% chance of the null hypothesis being wrong. Right? What's your null hypothesis? The null hypothesis is that all these elephants are healthy, because that's your comparative, that's the standard that you're using. Your data have come from healthy populations, and you're looking at some weight of an elephant and saying, how consistent is this with the reference population that I had, which is of healthy elephants. So there you might say that I'll take a larger chance of being wrong when I reject the null that this elephant is healthy. Right? So you might use some 10% level of significance. You might use different critical values. That will be minus 1.65 plus 1.65. On the other hand, if that's not the case, if the elephants are only cosmetically ill, right, they don't look nice to tourists, for example, right, they've got some skin infections which don't harm them at all, but they just look very unhealthy, so the tourist traffic to your forest reserve is falling, right? But once you take these elephants away and apply some some lotion on them, it takes a long time for them to heal, and it's very costly to feed elephants. You might actually not be so bothered about taking healthy elephants also to camps. Right? You will say only very, very bad looking ugly elephants I will take. Right? So then what you would say is, you would actually work with a smaller cutoffs. Say only I am willing to be wrong only 1% of the time. Right? So those are the choices that you make. Here we have predetermined for 5% mainly for pedagogical reasons. Now as you go on later on, you don't even have to make that decision. Right? As we'll, yeah.
When do we accept this hypothesis?
We never accept the hypothesis. Okay. Now let me come back and tell you. On the other hand, suppose I were testing a null hypothesis that mu was equal to 3.5 against an alternative mu not equal to 3.5. Rest of the things are the same. The hypothesis that I am testing has changed. Right? So what do you think will happen now? What part of this formula will change? Instead of 5, x bar will remain what it is. X bar is 3. 3.5. Yeah? Minus 0.5. So this is, yeah, minus 0.75. Now, does minus 0.75 lie outside this interval or within this interval? So what you are then saying is that if the null hypothesis is true, yeah, then I am quite likely to observe an x bar which is 3. If the population mean is 3.5, the likelihood of observing an x bar which is 3 is pretty high. Observing an x bar which is 3 is not so unlikely as observing an x bar of, for having a mean of when the population mean is 3.5 compared to when the population mean, the hypothesis population mean was 5. Right? So what we are really saying is the empirical support for the second statement is much higher than the empirical statement for the first statement. Given the empirical data, the first statement was much more unlikely to be true compared to the second statement. So here I say I cannot reject the null hypothesis that the population mean is 3.5. But that does not mean that I can accept the hypothesis the population mean is 3.5. Right? Look at it this way. Suppose I am not testing the null hypothesis that the population mean is 4. So when I am testing the null, that the population mean is 4. So what do I get? This becomes -1. Does it lie between -1.96 plus 1.96? Yes. So is the data that I got inconsistent with this hypothesis as well? No. So the data are not inconsistent with mu being equal to 3.5. The data are not inconsistent with mu being equal to 4. I can't accept both the hypotheses. I must be a total madman to say that mu could be 3.5 and mu is equal to 4 to accept both. I can't. All that I am saying is that there is a set of hypotheses which I cannot rule out at hand given the data. And there is a set of hypotheses which seem extremely unlikely given the data. Right? The ones which are extremely unlikely are being rejected because they seem to be that the fact that they are consistent with the data is very unlikely. And what do you mean by unlikely? You choose certain probability standards depending upon the costs and benefits of going wrong and right. Okay, so there could be at the same time several hypotheses which are consistent with the data simultaneously, which all of you cannot be accepted as true, right? So there are all the statements which you say you can't simply rule out of hand. Because what is the procedure? The procedure is we start with a hypothesis. When we are asked to test that hypothesis, we start with a hypothesis as tentatively true and try to see whether the evidence that we get makes at some point the hypothesis extremely unlikely to be true. Yeah, makes the hypothesis extremely unlikely to be true. Right? That's how hypothesis testing goes. Sure? Right? If you get sufficient evidence to say that the hypothesis is unlikely to be true, we reject the hypothesis. But the procedure is not designed to validate the hypothesis. It is designed to test the falsifiability of hypothesis. You know, there used to be a man called Karl Popper in the 1920s and the 30s and the 40s, who was actually a very, very famous philosopher, who used to belong to what is called the positivistic tradition in philosophy. And Popper said something very important. He said a statement is a scientific statement only if it is capable of being falsified. A statement is a scientific statement only if it is capable of being falsified. For example, if I say that this chalk will break if I drop it from a height of say 5 feet, is a falsifiable statement because I can drop it and see whether it breaks. Yes, it breaks. If it does not break, the statement is falsified. There is some way in which I can test this statement. Right? Whereas there could be many statements which simply cannot be falsified because you can't set up an experiment to test them. Yeah? Right? For example, I might have statements which are completely unverifiable. Right? Okay? Those can't be scientific statements because there is no way in which you can actually find evidence which will contradict them. Like all crows are black is a statement which you can falsify. Then you can start looking for crows. Right? And once you find a white crow, then you can say yes, all crows are black is not a correct statement, so crows could be black or white. So basic idea behind Popper's hypothesis was, the basic Popperian idea was that there is nothing called absolute truth in science. Everything is a hypothesis. Every statement, every scientific statement is a contingent statement which you hold temporarily to be true, and then you find whether you get evidence against that. When you get substantial evidence against that, you give that statement up and move on to a different statement. That's how science advances. Right? Therefore, this method of hypothesis testing is actually a statistical formulation of the Popperian idea of how to actually bring this, operationalize this idea. So here we start with a null hypothesis, and then we start by, trying to see whether we get enough evidence to contradict the null hypothesis. Okay, so it's going to be like that. Suppose I come here and ask you, suppose I start with the null hypothesis that this is Australia. Suppose I have landed from Mars somewhere in this country, right, somewhere, and then I was wondering what part of the world I am, right? So I see lots of people going out to cricket bats and all that, so I think Australians love cricket, so this probably is Australia. So I ask you, is this Australia? You say, no, this is not Australia, this is Mumbai, right? But I don't actually believe you, because any random person chosen could actually be out there to fool me. So I ask another of you. You say, yes, this is not Australia, this is Mumbai. A third person tells me this is Mumbai, this is not Australia. The fourth person also tells me this is not Australia. At some point of time I start wondering that there seems to be no evidence for my hypothesis. That everybody is telling me this is not Australia. So the evidence that I have is not consistent with my null hypothesis. The evidence that I have is not consistent with my null hypothesis. Therefore, I must give up the belief that this is Australia. Right? Sure? Okay. But just the fact that nobody tells me that this is not Australia doesn't mean that this is actually Australia. So even if I don't find evidence to reject my null, does not mean that this is null. This is that the null is true. For example, if I landed here at midnight and everybody was fast asleep, and if I thought this was Australia and I meet nobody who tells me that this is not Australia, doesn't mean I will continue to tentatively hold the hypothesis that this is Australia. But that does not mean that the hypothesis is true. For example, had I started by tentatively holding the hypothesis in Zimbabwe, I would have to hold it because nobody would have been there to tell me that this is not Zimbabwe either. So all that non-rejection of a null says is that we do not have enough evidence to reject the null. It does not mean that the null hypothesis is necessarily true. So we never accept a null. We either reject a null or fail to reject. Okay? So that's one question. The second question that I am going to ask you is, when I started with this, I said, okay, the null hypothesis of mu is equal to 5, so I said let that be the null hypothesis. The alternative hypothesis mu is not equal to 5. Ultimately, the null hypothesis was just a statement which I was going to hold tentatively to be true, and then try to see whether the evidence is consistent with that hypothesis. Do you think I could have also started with mu is not equal to 5 as a tentative hypothesis and tried to see whether the data are consistent with that? Because ultimately what is the process? It says you take some statement as tentatively valid and then try to see whether the data squares up with that. The actual data that you have, whether it is consistent with this hypothesis or not consistent with this hypothesis. Right? So what is the whole sanctity about starting with mu is equal to 5? Because my other hypothesis mu is not equal to 5. So why not start with mu is not equal to 5 and see whether the data is consistent with that? You see, when I said mu is equal to 5, it meant that x bar must be normally distributed with mean 5 and variance sigma square upon n. So therefore, x bar minus 5 upon sigma by root n must be a standard norm. So therefore, it should lie between minus 1.96 plus 1.96. So if it lies outside, I reject the null. If it lies inside, I fail to reject the null. But the whole thing was made possible only because of my assumption that mu is equal to 5. Suppose I started with mu is not equal to 5. Then x bar minus mu upon sigma by root n could have been anything. I would not even have got that number. And I would not have been able to test that hypothesis. Right? So it's because we would want to test hypothesis by a formal testing procedure that we start by having a null hypothesis that mu is equal to 5. Right? Okay, now what I'm going to do for you for a while, is that on? You guys know to switch that on? Is this remote for this? Yeah. Can somebody simply press that on button? Take a pen. Or try by your bench, that's perfectly fine. But where does the power to this come from?
He took the remote and walked out. He's texting.
Did he take the remote with him and walk out?
He has done the remote. We will wait for him to come back. Till now we'll only continue on this, and when I don't know why that's not working. Right? So minus 1.5. Sure? So will you reject the null or fail to reject the null in this case? Fail to reject. Take another example. Yeah.
What is a real life example which it says that we do not know the population?
In general, you don't. But still, this distribution is going to be very important for us. So, because we don't know that, we use other distributions like the T distribution. Right? Okay? In general, is right. In general, you don't know the population variance. So, we are making a strong informational assumption. But soon we will let go of that assumption as well.
And so one question.
Yeah.
Why don't we use the sample variance here in this case? The denominator.
Because we know the population variance. Yes. Because we are given the population variance. Had we not known the population variance, we will use the sample variance, but the distribution changes. Okay? Right. So now, let me test how well you understood this.
So, sir, now in this case we took mu is equal to 5. Can there be a case where we get for a population we take mu is between 3 and 5, like a range of?
Yes, you can do that. You can do that as well. Okay? But try to see, understand this. What do we have here? Let's look at this formula carefully. Yeah? What is x bar? So mu is your hypothesis. X bar is your empirical evidence. So x bar minus mu is the gap between the hypothesis and the empirical evidence. Right? X bar is what you see. Mu is what you hypothesize. X bar is the gap between what you see and what you hypothesize. Larger this gap, the more likely is the hypothesis, the less likely the hypothesis to be true. The larger the gap between what you actually observe, which is x bar, and what you believe, the more likely it is that what you believe is not true. Sure? That is the whole idea, x bar minus mu. So larger the x bar minus mu, the more unlikely it is. But then the whole thing is divided by sigma by root n. Why do you think it's divided by sigma by root n? Because you have to take into account the variability, the variations, possible variations in what you see. Because what you see is a variable number. What you see will depend upon the sample that you chose. So what you see is actually not a certain thing. It varies. So when you are saying, so what you see, the larger is the variability of what you are likely to see, the less is your ability to use that information to reject a null. Yeah? The less is the variability of what you see, the greater is your ability to reject a null for a certain gap between what you see and what you observe. Think of it like this. Suppose I have a cat, right? And my cat roams around my house, right? Normally the cat never goes, cats like to roam around the house. Normally my cat never goes, I know generally it doesn't travel more than 100 meters from my house. Suppose my cat is lost. So it's a black colored cat, it's lost. I get a phone call from somebody who stays in Andheri. So I put that on Facebook. I say I have lost my cat and please somebody find a black cat. Somebody calls her from Andheri and says that look here, we have found a black cat here. Is this yours? You would say that your cat generally doesn't go much beyond 100 meters from your house. So you would not really believe so strongly that this is your cat. Right? So you would say, I would come and see, but I think it is very unlikely that it's my cat. Whereas, if you have a cat which is a large roaming ground, which can travel anywhere from say Chembur to Goregaon, right? Okay? And then somebody calls you and says, the same person calls you up and says, look here, I have this black cat, could it be yours? You will have much more hope, no? Right? So you are starting with a null, that this is your cat, right? You are much more strongly likely to reject the null in the case of the cat just traveling 100 meters from your house, right? So what you have? You have the point where the cat was found and the point where you live. That's the gap between the actual and the observed. Right? The variability of the actual and the observed is much, the variability of the observed is much smaller in the first case. Right? So therefore, larger the variability of the empirical observation, lesser is the ability of that empirical observation to reject a null hypothesis. The smaller is the variability of what you empirically see, greater is the ability of a gap between what you see and what you believe to reject what you believe. Is this clear? Say for example, if I have to tell you